Good evening, all of you. Is the audio clear? And the video also? Please tell. So, welcome to today's session. So, in this session, we discuss about the homomorphism of groups. So, please take a note of that. It is a very interesting concept. If you observe, many of the questions are posed based on this concept. So if you clearly understand this module, the same module will go on to repeat as and when we discuss about the concept of rings. So there is a small interconnectivity between the homomorphism concept in groups as well as the homomorphism concept in rings. So this is one of the interesting things, and some standard results are also given in the previous year papers based on this homomorphism concept. So before going to start that, do you have any queries with regard to the previous session to anyone? Please say. Do you have any? All right. So first of all, tell me, are you getting any lag between the audio and video? Any one of you? Do you have like that? Or is it clear? Then thank you. So, if you go with the definition, let us take two groups G and G dash. Homomorphism is nothing but a function from G to G dash satisfying a property that f of AB equals to f of A dot f of B for all A comma B belongs to G. Please take a note of this. If f is a function from the group to group G dash, satisfying the condition that f of A dot B is equal to f of A dot f of B. So for every elements A and B taken in G, then we say that f is a homomorphism from G to G dash. So here we need to understand that the operation dot, what is mentioned here, should be clearly understood. One thing, on the LHS side, the operation dot is nothing but the operation defined on the group G. It may have plus, dot, star, circle, anything. So the LHS operation is by default nothing but the operation taken on G. Similarly, the dot operation on the RHS side is nothing but the operation on G dash. Okay? You please take a note of these things and tell me. So the main aim or main use of homomorphism is nothing but it preserves the structure between the elements. That's why we call it as a structure preserving function also. We can call like that. So it preserves the structure among the elements. In one way we can say that it maps arrangement of left hand side to the arrangement of right hand side. So whatever the structure on the right hand side, you can find a similar structure on the right hand side between the images. Okay? Is that clear to everyone? Please take a note of that. After noting, let me know. Right. Now, some questions will come into our mind that can you find a homomorphism always between the groups? That is one common question we always in search of that. It is always true that there is always a homomorphism between any two groups. That is, if you define the function as f of x is equal to identity for all x belongs to G. In one way, you can say it is a constant mapping, let us say. So if you take G here and you take G dash here, so every element is mapped to only one element. So if you pair the elements in this way, it always satisfies the criteria of homomorphism. Hence, this type of homomorphism, we call it as least homomorphism. Or you can also call it as a trivial homomorphism, but the appropriate word is least homomorphism, defining the way that f of x is equal to identity for every x belongs to G. So one thing, as per the terminology is concerned, whenever we use the symbol E, we have to understand that it is the identity element in the group G. Whenever E dash is written, it is the identity element in the codomain group G dash. That we need to understand that. Then two important things we have to understand is always the image of identity is nothing but identity. There is a small proof, but proof is not required for you. So always image of identity is nothing but identity. And the image of A inverse is nothing but f of A whole inverse under the homomorphism. Right? You please take a note of these things. So if f is a homomorphism, these two are the valid conditions. There are two more definitions we need to understand, and some definitions are also there. Once we finish with the definitions, then we go to the problem solving session. Right? And these problems are somewhat interesting for you also. So if f is a homomorphism from G to G dash, if f has additional property that it is a 1-1 function, then we call it as monomorphism. If f is a homomorphism with the property that it is a onto function, then we call it as epimorphism. If f is a homomorphism with the property that it is a bijection, so it is 1-1 as well as onto, in that case we call it as isomorphism. Now we give another names that if f from G to G dash is a homomorphism, then we call it as endomorphism. There is one more definition, we call it as automorphism. It is nothing but F from G to G dash is a homomorphism and it is a bijection. Please take a note of these definitions which are important while going for the next sessions. After noting, please tell. Here we need to understand that this is G to G dash. These two are nothing but two different groups. Here it is the same group. F is a function from G to G itself. Domain and codomain both are same. Here both are different. Please understand. That was the difference between these two. After noting, please tell. So whenever you consider a homomorphism from G to G dash, now what happens? In the domain you will have set of elements. For these elements you are applying the function, so you will get images in the codomain. So this is the image set. So this image set is formed by means of a homomorphism. So we call it as the homomorphic image. So how it is defined? F of G. You can also call it as image of F. Here F is a function. Im stands for image of the function. You can write it as either image of F or F of G equals to set of all images such that elements are taken in the group G. So for every element in G, corresponding image will be taken in the set F of G. So we call it as the homomorphic image. Another interesting definition is kernel of a homomorphism. This is one interesting definition. So how it is defined? It is denoted as ker F equal to set of all x belongs to G such that F of x equal to identity in codomain. This is very useful definition while solving the problems also. So how the kernel is defined? In the domain you are setting the images, I mean the elements. So for every element in G, you will get the corresponding images in the codomain. That is right. So among these elements, you are picking up those elements such that the image is identity for them. Those elements you are writing exclusively as a set, that we are calling it as kernel of the homomorphism. Okay. So how it is defined? In the domain, you are picking the elements for which the image is identity. Those elements are exclusively written separately as a set. We are calling it as the kernel of the homomorphism. Fine. So if once you have written them, then let us start with some problems which will be interesting for you. After noting, please let me know. Take the group as Z comma plus and another group as G dash comma dot. Dash is nothing but having two elements 1 and minus 1. Now the function is defined in such a way that so in this way I have defined the function. So please take a note of the problem. I have taken the group as additive group of integers. I have taken the codomain as the set having only two elements 1 and minus 1, and the operation is nothing but multiplication, the regular multiplication of numbers. And how the function is defined, whatever the integer you consider in the domain, it will be either 1 or minus 1, the image of it. So how the image is defined? If you take an even number, it is 1. If you take an odd number, it is minus 1. In this way it is defined. So you have to show that the function is a homomorphism or not. So we have to verify that whether it is a homomorphism or not, that we need to verify. Okay? Is the question part clear for everyone? Now, if you go for the property of homomorphism, not. Okay. So as I have mentioned earlier, while getting the condition of homomorphism, the left side operation is nothing but the operation on the domain. Right hand side operation is nothing but the operation on the codomain. So the actual homomorphism condition for this problem is nothing but f of x plus y is equal to f of x into f of y for all x belongs to G. So whenever you take two elements in the group, we have to verify this condition here. Now let us go with the procedure that, so I have taken the elements x and y in the group G. Please understand, I have taken the set as the set of all integers. So while taking the integers, as per the definition consent, we have different ways to choose the values of x and y. You can take both x and y as even numbers or odd numbers, or one value is even and one value is odd. In any way you can choose them. So whatever the way you consider, you have to prove that this condition gets satisfied by the function f, so that it will become the homomorphism between the two groups. Okay? Did you get the context now? All of you? Yes or no? Now let us take that in the first case, you take both of them as even numbers. Then what will be x plus y? Is it even or odd? It is even. Addition of two even numbers is nothing but even. Agree? As you are going to prove this condition, so I am going to calculate the value of LHS separately, the value of RHS separately. So if you consider f of x plus y, it is nothing but 1. Why? Because the function is defined in such a way that if the number is even, its value is nothing but 1. So f of x plus y is nothing but 1. On the RHS side, if you consider f of x dot f of y, since x is even number and y is even number, there is nothing but 1 dot 1 equals to 1. So in the first case, you can say that this condition is satisfied by f. So any queries for anybody in this part? Please tell. Or is it clear? Now, take the second case that both values are odd. So I have taken in the domain two values x and y and both are odd. Then in that case, x plus y is nothing but even. Because whenever you add two odd integers, the result is an even integer. Therefore, if you consider f of x plus y, its value is nothing but 1. If you consider f of x dot f of y, it is minus 1 dot minus 1, so value is 1. So in this case also, this condition is satisfied by f. F of x plus y is equal to f of x dot f of y. So I have taken f of x, f of y because f of x is odd, hence x is odd, so f of x is minus 1. Since y is odd integer, f of y is minus 1. So on the product, you are getting 1 as the result. I hope that you can find the third case on your own, where you take x as even and y as odd. You can take any one of them as even, other one is odd. So you can verify that whether this condition is satisfied or not. So in that case, you get that on both hand side, minus 1 equal to minus 1, hence the equation gets satisfied. Please check on that and confirm your result. If everyone finished it, then I take the next level. Now, for this problem, if you think about that, is the function 1 1 or not? Can you tell? Is it a 1 1 function or not? I think everyone will know the definition of 1 1 function. I hope so. The general definition will be given as different elements will have different images. This is the definition of 1 1 function. All of you agree? Have you known this or not? Now, while proving this technically, how do we do? Actually, if you want to say that a statement P implies Q, technically we prove that negation of Q implies negation of P, because these two are equivalent. So, while proving this thing technically, apart from showing like this, we prove that if we say this is P and this is Q, we can say that if images are same, implies elements are same. So while proving this problem, while proving the problems, whether it is a 1 1 function or not, we use this kind of technique. If you take that two images are equal, then you have to show that the corresponding elements are also equal. So this is not a 1 1 function, because as you have taken f of 4 and f of 6, both have value 1 because they are even numbers. But 4 is a different number and 6 is a different number, hence it is not a 1 1 function. That we can clearly understood that. Now other question comes that, is it an onto function? Is it an onto function? Yes, because if you think fundamentally, onto function says that whenever you have a function between the two sets, if you take an element in the codomain, for this you should have at least one preimage here. Here so many preimages are there because the codomain contains only two elements, 1 and -1. So for 1, the preimage is nothing but so many even numbers are there. For -1, the preimage is nothing but so many odd numbers. So it is always a onto function. Okay? We accept that or not? Any questions or doubts for anybody? While understanding the nature of this function? Tell. Now, I have given some definitions based on the properties of homomorphism. So as per the properties considered, among the categories what I told you earlier, is it a monomorphism, epimorphism, isomorphism? Under which category this function comes? Is it a monomorphism or epimorphism or isomorphism? Which one is correct? Epimorphism, because it is just satisfying only onto and homo, not the 1 1 property. Now, if we discuss one more thing, what could be the kernel for this function? What could be the kernel for this function? If you want to calculate the homomorphism, the kernel value. Yes, that is true. So as we define that, kernel f is given by set of all x belongs to G such that f of x is equal to identity in G dash. So here G is nothing but set of all integers. So this is nothing but set of all elements in the integer set such that f of x is equal to 1. Because in the codomain it is having only two numbers, 1 and -1. The operation is multiplication. So what is the identity element with respect to dot? It is nothing but 1. So you are selecting the elements in the domain such that whose image is nothing but 1. So it is possible from the definition that if you take an even number, then only it will come. So this is nothing but set of all x belongs to Z such that x is even. So set of all even integers. This is the kernel value for it. So is everyone clear over this part? Let me know. So this is the complete discussion with regard to the definitions, how to prove homomorphism, how to calculate kernel, etc., etc. Now let us move somewhat theoretical. Some result-oriented things we will do. So which gives a good idea over this concept. And in this chapter we are going to prove one good theorem. We call it as a fundamental theorem of homomorphism. So it gives very good understanding and so many problems are there based on that. First of all, if you take that f from G to G dash, a homomorphism, then kernel f is a normal subgroup of G. This is one result which you need to understand. Please take a note of this, which we will discuss now how to prove this. So if you take a homomorphism from G to G dash, then the kernel of the homomorphism is always a normal subgroup for the domain. Now how to prove this? First of all, I will read the definition of the kernel. It is defined as set of all x belongs to G such that f of x is equal to identity in the codomain. So while proving the result, you know the hierarchy. So we have to prove that kernel f is a non-empty set first. Then we have to prove that it is a subgroup. Then we have to prove that it is a normal subgroup. This is the hierarchy we need to show as per the solution is concerned. Now, can you say, is kernel f is non-empty set always? So why? Because in the beginning of the session, I have mentioned a result that always image of identity is identity. That is one result I have mentioned. And image of the inverse is equal to image whole inverse. So as per the result is considered, always you will get one element in the kernel, because here E stands for identity in the domain, E dash stands for identity in the codomain. So if you observe the definition of kernel, you are selecting an element in the domain whose image must be identity. So as you know that identity element belongs to the group and f of E is equal to E dash. So kernel f is non-empty. There is the solution for the first line. Clear to all or any questions? So coming to the second criteria, How to prove that it is a subgroup? What are the procedure I need to apply here to show that kernel F is a subgroup? Or generally think that whenever I have a set, if I want to show that it is a subgroup, what are the procedure I need to follow? Yes, you are going to apply the necessary and sufficient conditions. So if I take two elements x and y in kernel, I have to show that xy inverse belongs to the kernel. So if I have shown this condition that as per the necessary and sufficient condition, kernel F becomes the normal subgroup. Now let us take the two elements here. So let us take x and y in the kernel. Now observe the definition of kernel. If I want to show that x belongs to the kernel, its image must be identity. If I want to show that an element A belongs to the kernel, its image must be identity. Similarly, if I want to show that xy inverse belongs to the kernel, I have to show that xy inverse image must be identity. Did you get the context? Yes or no? I repeat that again. So if I want to show that L belongs to kernel, for this I have to prove that f of L is equal to identity as per the definition of kernel is considered. Is everyone clear? Similarly, if I want to show that xy inverse belongs to the kernel, I have to show that f of xy inverse is nothing but identity. So for this, I am considering f of x dot y inverse. So this is nothing but, since f is a homomorphism, you can write it as f of x into f of y inverse. This is equal to f of x into, as I have given, from this condition I have to write, I can write that f of y whole inverse. Please understand, initially you have taken x and y in the kernel. So from the definition of kernel, you can write it as identity dot identity inverse. Because f of x is nothing but identity, f of y is nothing but identity, because x and y are taken in the kernel. Since inverse of identity is nothing but identity itself, so this is nothing but identity. Therefore, this condition is satisfied by kernel F, hence it is a subgroup. Please take a note of that. Then we discuss about the normal subgroup. It is also very simple. If you draw the picture for our understanding, so this is G, this is the kernel. So what I have to show, if I take any element here and x inverse in the group, so I have to prove that x inverse belongs to the kernel. So if I have shown this, it becomes the normal subgroup. So for this, you consider f of x inverse. Since f is a homomorphism, you can write it as f of x, f of a, f of x inverse. Since a is taken in the kernel, this value is nothing but identity. So this is nothing but f of x into f of x whole inverse. So this is nothing but identity. Because element and its inverse, whenever you multiply together, you will get identity. Therefore, this value belongs to the kernel, hence it is nothing but a normal subgroup. So please take a note of that. After noting, please tell. Now, one interesting property about this is please take a note of this one. If f from G to G dash is a homomorphism, then f is a 1-1 function if and only if kernel f is nothing but only single element set identity. So except identity, there will be nothing in kernel f. Then the function becomes 1-1. Is the concept clear for everyone? What we need to show? So since it contains main part as well as converse part, let us prove them together. Suppose you assume that f is 1-1. So you have to show that kernel f contains only one element. So the objective here is, let me say, I have taken a set in which every time I am picking up an element. So whatever the element I am taking it out, I am always getting an even number. So what does it mean? Always I am taking out as an even number. So what does it mean? Are you getting the context or not? I repeat this again. Suppose you take a basket. Every time I am picking out a ball from the basket, always it is coming out as a red color ball. So what does it mean? So every time, as and when I am taking out a ball, it is becoming as red. So the box totally contains only red colored balls, isn't it? Yes or no? Every time I am trying to take a ball outside, it is always becoming red. So every ball, whatever I am taking that out, it is becoming red. It is nothing but the box totally contains red colored balls. Say. So similarly, here also, to prove that kernel f contains only one element, so every time I am taking an element from kernel, it is becoming identity. So what happens? Kernel f is containing only one element, that is nothing but identity. That is the motto behind this concept. Okay? So you take that x belongs to kernel f, be any element. as per the definition is concerned, it is nothing but f of x is equal to identity as per the kernel definition. So this you can write it as f of x is equal to f of e, because you know that f of e is nothing but e dash. So from this very step, you can say that x is equal to e because it is a 1-1 function. So what is meant by 1-1 function? Whenever images are equal, then elements should be equal. This is the concept of 1-1 function. So what happened now? I have taken an element in the kernel. It is any element in the kernel and it is becoming identity. So what happens? Kernel is nothing but only identity element set. No other element is there in the kernel F. Is the logic clear for everyone? The strategy, how we are going to prove? All of you? Right? Now let us go with the converse part. So you assume this condition. Now we have to prove that F is 1-1. The traditional method is we take elements whose image is equal. So we have to show that the elements are equal. The thing is, you take two elements such that the images are equal. So I have to show that x is equal to y. That is my intention. So this implies that you can write it as f of x into f of y whole inverse is equal to f of y into f of y whole inverse. So what I am doing? I am multiplying both sides with f of y inverse. So from this you can say that f of x into f of y inverse is equal to identity. Because this condition I already mentioned how it came. Since f is a homomorphism, you can write it as f of xy inverse equal to e dash. So please tell up to this step you have any confusion or not. Please take a note of that. After noting, please tell. Now, immediately I can say that if we observe clearly that xy inverse is an element for which I am applying the function f, the result has become identity. Immediately from the definition of kernel, we can write that xy inverse belongs to kernel f. Do you agree or not? It is nothing but the definition of the kernel. How the kernel is defined? Set of all elements whose image is identity. As we have considered that kernel F is having only one element. So from this you can say xy inverse is equal to that element E. You have no other option because the set is having only one element. So multiplying both sides with y, you can say that x is equal to y. If you multiply both sides with y, you will get x equal to y. Therefore, I have taken that images are equal and I proved that elements are equal. Therefore, f is a 1-1 function. So please take a note of that. After noting, please tell. So are these results interesting for you or getting confusion? If you understand the definition clearly, then it is very easy for you to get connected with the result. So if you didn't understand the thing, then you totally miss the concept. Actually, there is nothing in the result. It is just based on the definition. Here you take the definition of 1, 1. You proved that kernel is having only one element. There you considered kernel having single element and you have proved that it is a 1, 1 function. Nothing else. You just used the definition, the concept of definition. That's all. Any other queries for anybody here? Now I start a new concept, the very interesting theorem. Shall I continue? Right? Now the theorem what we go on to discuss, we call it as fundamental theorem of homomorphism. There is another name for it. We also call it as first isomorphism theorem. Actually, there are 3 isomorphism theorems. Among this is the first one. It has 2 names. We call it as first isomorphism theorem or fundamental theorem of homomorphism. Now the statement is given by so this symbol we call it as isomorphic symbol. So how it is written? We write equal to sign and we use tilde. So we write S horizontally. So this symbol we call it as isomorphic symbol. So it has another equivalent statements that also we take into consideration. So all these 3 statements are equivalent. So the statement of the theorem, we can write it in any manner. All are similar. The procedure or the way what we are going to prove is very similar. No change at all. So whatever the way the statement is asked, the proof is only 1. No change at all. So first of all, read out the statements. So we prove the theorem based on 1 and 3. Second, I will show you how to prove it. Okay. So please read the statement first. Understand the essence. Then we start discuss how to prove that. So different authors will use the terminology differently. But this is the types of statements available for fundamental theorem of homomorphism on groups. You can take any variety on them, but they have the equivalent feature in the proof style. After noting, you please tell. So all of you noted that? Okay. Now, I will erase the statements. So, the outline is very simple. I took two groups, G and G dash. By default, I took a homomorphism F between them. Okay. So, which sentence you want to write, I will tell, I will dictate that, you can take a note of that. First, second, third, which one you want to write? Among the three statements, 1, 2 or 3. So have you noted the first two statements of the fundamental theorem? You want to write a third one, or you have noted them completely? All right. So here I took a homomorphism between two groups, and it is onto function also. It means for every element in the codomain, I will get an element in the domain. Now, my intention is I have to show that G by kernel F is isomorphic to G dash. This is the intention of the problem, a theorem you can call. So for notational convenience, he used the symbol kernel F is equal to K. So every time writing kernel F gives me a confusion while reading the proof. So I am using a symbol that K stands for kernel of the homomorphism. So as per the theorem statement considered, I have to show that G by K isomorphic to G dash. This I want to prove. Okay, all of you? Yes or no? Now, if you observe, here we got two groups. This is the group G dash given in the problem. And can you say the name of this group? What it is actually? There is a specific name for that kind of notation in our problems. Can you tell? we call it as dash. I will give a hint. If you write like this, we call it as the name. What is the name of this type of set? We call it as? Can you recollect? All right. So we call this with the name quotient group. Can you recall the definition I have given in the previous session? I hope so. All of you? Say. Can you recollect that or not? So if you observe that, how a quotient group will be formed? You should have a group and you should have a normal subgroup. So whenever a group and normal subgroup are given, then we write G by H. It is nothing but containing all cosets. The set of all cosets formed by H with respect to G. So we call it as a quotient group. Another name for it is, we also call it as a factor group. Now you should have a doubt that is G by K a quotient group? So immediately we should understand that if you want to form a quotient group, all we need to have is a group and a normal subgroup for it. In the previous theorem, we have proved that kernel F is always a normal subgroup. We have proved the hierarchy model. So as per that result is concerned, we have a group G, we have a normal subgroup K, hence G by K is nothing but quotient group. It always contains the cosets. If you talk of precisely, G dash is the codomain containing images. G by K is the quotient group containing cosets. Okay? Clear to everyone? So here the operation is multiplication. Here also the operation is multiplication. So if you want to prove that these two groups are isomorphic, what is the definition of isomorphism? We should have a function between the two groups and we have to prove that the function is 1, 1, on 2 and a homomorphism. If the function satisfies the three criteria, then we say that it is an isomorphism. So all we need to show is we have to build a function between the two sets and we have to prove that the function has the three properties 1, 1, on 2 and homomorphism. Hence it will become an isomorphism so that these two groups will become isomorphic. Clear for everyone? The context we are going to prove? Say. Yes or no? Now, first of all, we need to define a function between the two sets. So let us take the function g. How I am defining? G from G by K to G dash by G of Ka, you can write like this, or you can also write it as Ak also, right? Equals to f of A. Please understand how the function is defined. It contains all cosets. So in the domain, I pick up a coset. How the coset is paired with? It is paired with the image of the element for which the coset is formed. So A, f of A, because G dash contains only images. What kind of images will be there in G dash? It contains only F images. It contains only cosets where the elements are taken in G. So G of K of A is equal to F of A. This is the way I am defining the function. Any confusion for anybody in this definition? How we have arrived with this part? Please tell. Yes or no? Are you getting the ideology or not? Right? Now we prove that this function is 1-1 onto and homomorphism. So first the function is 1-1 and also it is well defined. Well defined is nothing but we can define the function this way. So let us take two cosets So I have taken that two images are equal. So I have to prove that corresponding elements are equal to show that it is a 1-1 function. So from the definition of G, you can write it as f of A equal to f of B. Now for this relation, I am multiplying both sides with f of B inverse. So on the left hand side, functions is for f or G. Please understand, f is the given function in the problem. G is the new function you are defining between the two groups, G by K and G dash. And you have to prove that the new function G is 1-1 onto and homomorphism. So that G will become isomorphism, hence the two groups will become isomorphic. Clear to all? So on the LHS, you can write it as f of A dot f of B inverse. This is identity, because you are multiplying an element with its inverse, so it becomes identity. Since f is a homomorphism, you can write it as f of AB inverse. Now understand that this is an element for which I have applied the function f and the result is identity. Therefore, from definition, AB inverse belongs to kernel f. For this, I have given a name K. Therefore, what you got? AB inverse belongs to K. Immediately, I can write that KA is equal to KB. Now the question comes, how it happened? So this thing happened because I have given some results in cosets like AH is equal to BH if and only if A inverse B belongs to H. HA is equal to HB if and only if AB inverse belongs to H. Can you recollect these results from the cosets chapter? So using this part, since Ka is equal to Kb if and only if AB inverse belongs to K, this thing will come. And if you observe that the logic what I have written is implies and implied by. So this is so if you start reading from this step, if this is correct, then this will follow, and so on. All will come. Therefore, the function g, what we have defined is 1, 1 and well defined. Okay? Is it clear to all how I have proved that it is a 1, 1 function? Please take a note of that. If you have any questions or doubts at any step, you please ask. So the underlined idea is, if you want to prove that two groups are isomorphic, you should build a function between the two sets and you have to prove that the function is an isomorphism. That is, it becomes 1, 1 onto and homomorphism. That is the ideology. Please take a note of this, then let me know. So here we need to understand that I already mentioned that all the definitions and some important theorem results must be known to you. Otherwise, you cannot solve the further sessions, because here at this step, I have used this part here. Okay? So what is the reason for this step? This step is taken because of this condition. Right. Now, I am going to prove this. It is a homomorphism. The function g is a homomorphism. So you take two cosets. Now you consider g of Ka dot Kb. So this is equal to g of Kab. Because how do we multiply two cosets? The set will remain same. We simply multiply the numbers, the elements. This equal to f of ab. How this came? Because this is the definition of g. Whenever you got a coset, for the element you apply f. This is the definition of g. So this is the set k. This is the element AB. For this I am applying f. Since f is a homomorphism, you can write it as f of A dot f of B. If you have a doubt, you can write it as coset multiplication. Since G definition, since f is homo, again you can write it as g of Ka dot g of Kb. Since G definition, therefore G is a homomorphism. Because what is the definition of homomorphism? We have to show that f of xy is equal to f of x into f of y. So whenever you take two elements product inside, it is equal to the individual product. So this is the two elements product. It is equal to individual product. Therefore, it is a homomorphism. Clear? Please take a note of this. Then we go to the last part, that is, it is an onto function that we prove. Shall I continue? Is that noted? Right. Now, this is an interesting situation. How to prove that G is onto? So for this, I request you to write the diagram. The diagram gives you very good understanding. Now, what is meant by onto? For every element here, you should find an element here, so that if you apply G, this element should come. Agree? Yes or no? The concept of onto. For every element in the codomain, you should find an element in the domain. That is the concept of onto. Accepted? Right. Now you give a symbol for the codomain. You give some number, some name. Can I take the symbol Y in the codomain? So I will write Y. So I take Y belongs to G dash. So actually, in the problem it is given that f from G to G dash is onto. So it means for every element in G dash, you should get an element in G, because the function is onto and homomorphism. Accepted? Say, as per the problem statement is considered. So for every element in G dash, you will get an element in Z, because the function f is there. So I will take some name here. I will take the name A or X, I can take. Any questions for anybody in this step? Yes or no? If you have doubt, you ask right now. Right. Now, understand the relation between group and quotient group. So how the quotient group is formed? You take any element in the group, multiply, then you will get the quotient. It is in the quotient group. So what is the relation? You can say, if I have written G by H and G, if I take the element A here, the corresponding quotient is HA. If I take B in the group G, corresponding quotient is HB. If I take 1 in the group G, corresponding quotient is H1. because this is the interconnectivity between group and quotient group. For every element here, corresponding quotient will be here. You have calculated the quotients also, right? Similarly, for every element here, corresponding quotient will be here. So here the quotient is kx. So this implies kx belongs to G by K. Therefore, if you consider G of kx, it is nothing but f of x, it is nothing but y. Therefore, the function is onto. So for every element in the codomain, I will get a quotient in the domain such that G of kx is equal to y. Therefore, G is an onto function. So in this theorem, onto is somewhat interesting and typical to get the idea. But I hope that that diagram will help you to understand. Clear? So I will give the idea that you take a double implies here. So this gives the idea. So here we have started, come like this, and this proves the onto part. That's why while writing the diagram, I have taken the symbols like this. Any counter questions for anybody here? Please tell. Yes or no? Therefore, we have proved that G is 1, onto and homomorphism. Therefore, it's an isomorphism. Therefore, G by K isomorphic to G dash. The proof is complete. So if you observe that I have mentioned the theorem in 3 different ways. Whatever the way is there, this is the standard proof. There is no change. Suppose if you take the second statement, in the second statement it is given that every homomorphic image of a group is isomorphic to some quotient group. So their onto condition is not mentioned. So in a simple manner, the same proof you write without changing any step. So in the mapping, you define like this. In the place of G dash, you simply write f of G. Remaining part is totally same. There is no need to change a single step in the proof. You simply, in the mapping definition, apart from taking G dash, you take f of G. That's it. Okay? Are you clear? So, if you want to write the third part, in the statement I have given the third statement, where it is given that if phi from G to G dash is an epimorphism, then G by kernel phi is isomorphic to G dash, right? For this also you write the same proof, no change at all. In the mapping, you just write like this. Take kernel phi is equal to K, define G from G by K to G dash as G of K is equal to f of A. Just you do the modification like this. Every part is same. Wherever f comes, you replace with phi. That's all. So in the total proof, you replace f with phi. That's all. The same proof you will write, no change at all. Just changing the symbol. So apart from defining G of K is equal to f of A, you define phi of A. In the whole proof, apart from writing f, you write phi. That's all. The same proof will come. So if you understand the logic, so whatever the pattern they will give in exam, this is the way to solve this. Okay, all of you? So at this part, I want to conclude our today's session. Thank you very much for your good cooperation. and we will resume tomorrow. If you have any other questions with regard to this theorem, you can ask. Because it seems to be really complicated in the beginning time, but once you go through the proof 1 or 2 times, just today night itself you just read them, you just read it 1 or 2 times, then you will get hold of the whole proof. I will say, so I have given the task that you write kernel phi is equal to k, define g of k is equal to f of a. So wherever f is there, you replace with phi. So you try for the third part. You prove the theorem using the symbol phi wherever f is there, so that you will get the idea, the whole scenario of the part. Then there is no need to by heart the theorem separately. You can prove it on your own. Then you can take it as an assignment or practice, whatever you can call. Clear? Then that's all for today. If you have any other questions, you can ask. Right. Thank you.